Okay. Hi, everyone. My name is Asan. I'm a senior data scientist at RBC, and I'm very happy to talk to you about this very interesting paper on the topic of multitask learning today. I was mentioning before this started that it's very interesting. These days, every now and then an architecture comes about and becomes this new surge in the field, sort of to the point that almost putting aside every other algorithm that was there and redefining the field. And right after, you see a new surge into, okay, how efficiently we can now use this new architecture. We had previous talks on self-attention, transformer networks, GPT-2 specifically, that also talked about the similar architecture. This one is how to use it specifically, and not yet another one to use it efficiently and specifically for multitask learning, again, in natural language processing. Okay, without further ado, we start the talk. The topic is linguistically informed self-attention for semantic role labeling. So the main purpose is SRL, but to achieve SRL, semantic role labeling, it also learns the entire linguistic natural language processing pipeline necessary to perform SRL. This paper has been written by people at UMass and Google, as you see on the screen. Well, I'm presenting this talk, and Masood, also senior data scientist from RBC, will be facilitating the talk. All right, so let's talk. So if you see something, it's because we're not using PowerPoint, and it was created on PowerPoint. So I'll translate what they mean. So that is semantic role labeling compressed into that representation. So what is semantic? How many people here do know what semantic role labeling is by show of hand? Okay, if you do. It's traditionally understanding language was discovered in layers. So the first layer, you would understand the phones or phonemes, the sounds that you're making and what they mean, what the representation of which in your brain. Then you go to the words, morphology. Then you go to to how these words relate to each other, so syntax. And then you would go to the semantics, which is a layer on top of syntax. And this understanding of this is very important to this work. So I'm going to elaborate a little bit upon. So in syntax, you got entities such as verbs, nouns, and subjects and objects, right? So an object could be, I don't know, Raj was attacked by someone, right? So someone, well, that wasn't, let me see. So Raj, in this example, is the subject, right? Syntactically, it's a subject. But did Raj do something or something happened to him? So obviously Raj was attacked, so something happened to him, right? So it's the receiver or theme of the action. Although it's a subject, right? Although it's a subject, he was objected to some action, right? He was subjected to some action. So that's why the semantic roles, what was done to whom, don't always necessarily match or map to the syntactic roles, which is verb, object, and subject. So specifically for this example, object and subject can switch places. So that's why with this entire field of semantics and linguistics is defined based on these semantic roles. And in NLP, we try to automatically capture those. So agent is the doer, for example. Patient and themes are objects or people that receive some actions, so on and so forth. The list goes on, but let's just usually theories limit to some, not all the roles. So the goal of semantic role labeling is to find out what each word, what semantic role each word in a sentence takes on. All right, let's go. So that's context, and so the SOT, state-of-the-art framework tackling this work is a deep architecture. Surprise, surprise. And it's also a self-attention architecture, right? But it doesn't necessarily use any syntax, right? That architecture is basically a self-attention architecture. We do a quick review of it, although we have quite a few videos on self-attention on AISC's website. If you want to go look at it, AISC.A-I.SCIENCE. But we'll review it very quickly. So it has been shown, although, that if you provide gold syntax trees to previous algorithms, not much self-attention specifically, although I think a couple of instances are there, the syntactic trees can improve the performance for older architecture quite substantially. What it means is that our deep architecture, so all of these are, most of these are deep, at least the recent ones, are deep architectures. So either LSTMs, RNNs, a variant of RNNs, or nowadays self-attention. So it's been shown that for the older models, adding good syntactic trees, so informing the model about the actual syntax of it, whether gold or very well predicted by a parser, will substantially improve the performance of the model. Okay. So LISA is a solution to that. So linguistically informed self-attention is to do a similar thing for self-attention. Given that self-attention already performs or outperforms every other method out there, the hope is this augmentation will result in an even better performance in self-attention networks, tackling semantic role labeling. That's LISA offers. Multi-health self-attention, POS tagging, predicate detection, dependency parsing, and SLR all at the same time and in parallel, almost in parallel. SLR is the very last layer. So why is it important? So traditionally, either machine learning NLP or the era before that almost, as well as deep NLP to some extent, NLP was pipelined. So you start with probably tokenization. Well, you start with fixing your encoding. Then you go ahead with tokenization, perhaps sentence tokenization first, then word tokenization, pass it through your maybe POS tagging or parsers, either pipelined or at the same time, or just parsers. And then from there, inferring semantic role labeling, what semantics is going on, and then doing downstream tasks, such as, I don't know, sentiment analysis, or any other more high-level tasks you have. So that's very pipelined, right? The problem with that is the error can always propagate. And in the latest model that you're building, you have no control over the earlier errors, right? And that's a big issue. Also, it's a linear approach. You have to always do parsing first, then SRL, so on and so forth. OK. Yeah, all right. So one attention head is devoted, and this architecture is devoted to attend, as we'll see in detail, attend to syntactic parents. I think I'm missing an R there. Gold and non-gold parse trees can be feasibly integrated into the system during inference without retraining, and that's very that's a substantial contribution. We'll see how it is, but basically what it says is, okay, we used this parser either integrated in our system or external during training, right? And now, during test time, we realized that there is this better parser out there. What we can do is just totally get rid of our parser, disregard whatever it predicts, or make it predict the results of this other parser that we have. So if someone else at MIT, at IBM, or at Stanford, U of T builds a better parser, I can keep everything in the model intact, just add that parser. I really like this modular design, and it was wonderful to see. Very excited about it. So, and it's obviously the new state of the art. OK, let's see if I can decode this one too. SRL helps. OK. So SRL traditionally is extensively used in dialogue systems. Machine reading or machine comprehension or reading comprehension. I need my slide. beautiful. And machine translation. So machine translation also nowadays is mostly end-to-end, but traditionally, as I mentioned, these pipelines have been used. And even nowadays, usually better informing of a lower-level syntactic information almost always results in better performance. Aside from a domain in NLP that deals with really challenging semantic work, such as co-reference resolution, bridging co-reference resolution, those are a little bit harder to integrate things in. Okay, so and among other tasks. Thank you for resolving the encoding issues. So emergence of deep neural nets. So recently, deep pure architectures, as I mentioned, have outperformed syntactically informed methods of previous architectures, not self-attention. I mentioned earlier SOT with no syntactic. The current SOT does not use any syntactic information. Deep methods, input is usually raw tokens, often with predicted predicates. And predicates are technically, you can think of them as verbs. They're a more inclusive set. So they can include nominal predicates. So they're technically, their syntactic role is a noun, but they're still a predicate. They're still affecting other arguments in a sentence and make them look like objects or subjects. The details of which we can talk later or during the discussion. But right now, for simplicity, think of predicates as verbs, right? What the verbs are. Yes, and this contrasts to an entire pipeline of NLP that as I talked about a little bit earlier. Okay, so a major source of error with analysis done in specifically 2 major papers in the past shows that if you add syntactic information, as I mentioned earlier, it really helps. Also, most of the confusion about the errors that you make in semantic role labeling is caused by an insufficient understanding of syntax, right? Specifically, PP attachment. I had a good slide on it. I'm not sure how I missed to present it here, but basically, PP attachment or prepositional phrase attachment is. Oh, actually, I think I have it. There you go. Okay, so it's what is it? Sherlock saw a man with binoculars, right? It could mean Sherlock using binoculars saw a man, or it could mean Sherlock saw a man that. Like whom was using or who was using binoculars, right? So this is the PP attachment. For humans, it's almost unresolvable. Same for well, in this scenario. Same for machines, but there is always contextual information can lead to resolving this issue. But also, not all of PP attachments are this ambiguous. Actually, most of them aren't really that ambiguous. This is the 100% ambiguity. Most of them are humans, by looking at the context, can really understand them. I think in one of the self-attention talks, we have this example. I'm not going to repeat it. Look at those. It involves probably a wide raccoon or road. A wide raccoon or something crossing the road, so where wide refers to the road, not the raccoon. But look at it, I almost butchered it. Okay, so parse quality. So obviously, if you, as mentioned, if you increase the parse quality, you hope that it would work better. I mentioned these 2 works earlier on. A couple of works have been done in this space with regard to parses coming from parsers. So parse trees coming from parsers. It does improve, but almost minimally improves the performance. And sometimes it's been shown if you add a gold standard, it substantially improves. But the latest work uses a gold parse trees with a graph CNNs by these people, result in a slight improvement. But it doesn't perform well on. Yeah.
Can you just go over what gold standard means?
Oh, yes, thanks for the question. So when I say gold standard, oh, the question was what's gold standard? And when I say gold standard, it means usually human labeled labels or annotation, right? That we look at them as the correct annotations as opposed to labeling done by high accuracy or even low accuracy machines, right? Those are predicted, when I say predicted. Thanks, great questions. Feel free to ask any clarification questions, yes?
So these two methods already perform better than the syntactically informed methods that are not deep?
So these two are technically syntactically informed. The state of the art is not using self-attention, is not using, syntax at all. It's using pure self-attention, which this work is built upon. These two use syntactic information. Sometimes they improve upon the performance. Sometimes, for the case of out-of-domain data, they damage the performance. Even the improvement using syntactic information is not always substantial. Most of the time, it's actually not that significant, right? So, so the goal of this talk is to utilize this syntactic information to the fullest, right? That's the goal of this work. Okay, so an overview of LISA. It's a multitask learning framework. It encodes only once, so similar work in the past. They detect or use the detection of predicates, which we can loosely refer to them as verbs. Okay, you have those, and then per predicate in the sentence, which could be multiple. You can have multiple words in the sentence. I saw John, who saw I don't know, Mary, right? This is the entire thing is one sentence. Each predicate then has its dependencies, right, and can be dependency parsed separately. So, for example, in that embedded sentence that I mentioned, I saw John who saw. John would be the object, for example, of the first sentence, and then who saw Mary, for example, Mary would be the object of the second predicate, which is John, right? Which its subject is John. Okay, so they take each predicate and encode them separately. By encode, probably the entire pop line. Bring it to embedding space, doing self-attention on it, and deciding what the dependencies are. And dependencies, let's think of them as objects and subjects for the simplest case. But syntax is much more complicated, right? There is instruments, prepositional phrases, and so on and so forth.
Since LISA includes the whole pipeline where you take a word and you put it into embedding space, can you apply LISA to other languages automatically? Because you just treat the words and then you do everything from there.
Potentially, yes. That's a good discussion point. Let's get back to that in the discussion point. But potentially, yes, because in deep learning in general, you only have your token representations, and that should be enough. If the language has a parser, for example, then it obviously will help. Because the limitation then, this framework uses parse gold standards, right? Meaning that for any language, where if it's under-resourced language, meaning that we do not know the syntax of it, therefore we can't have labels for them, then this architecture probably boils down to its pure sense without using much of the gold standard syntax. But still, it can. I believe it can work. Let's get back to this the discussion. Yes.
Sorry for interrupting you. So when I was reading the paper about this part, I'm not sure if you're going to explain more about it or not, multitask learning. So it was mentioning that like LISA is able to detect like different predicates in a let's say like a set of tokens, but those predicates could be a part of a speech as well, right? So it was saying that if a token is a predicate and also part of a speech, LISA is able to distinguish between those two. So is it like a multi-label task, or is it like something different that I was not able to understand?
Yes, I'll cover those.
Okay.
And I just have to say, for the sake of accuracy, I don't think that's the right interpretation. I will tell you what it is, actually. It's a joint prediction. Okay. Thanks for the questions. So overview, it does multitask learning. We'll know what it is momentarily. It encodes only once, as I mentioned, as opposed to other. And again, another correction. So I don't like to think of it as a pipelined approach because it's parallel. So when I say pipelined, I mean sequential. So you do your semantic, you do your tokenization, then you do your POS tagging, then you do your parsing, then you do your semantic rule labeling. But the architecture is doing all of them at the same time, right? Okay, so it uses stacked multi-head self-attention. We briefly overview that as well. End-to-end predicting in parallel. Sorry for the quick interruption. So basically, we're overviewing Lisa and its architecture. It's multitask learning. I just explained that it doesn't encode every predicate in a sentence separately, which is computationally more efficient, stacks multi-head self-attention layers, and does end-to-end predicates, POS, attention to syntactic patterns, as well as semantic rule labeling at the same time. All right. We'll see. Yeah. Oh, OK. Thanks again. If I gloss over any term, please ask. POS is part of speech, yes. That means what is verb, what is noun, which one is noun in a sentence, which one is adjective. So those are parts of speech. They're on the syntactic layer. But it doesn't really say what is governed by what. And by that I mean if you have a verb and there you have an adjective, there you have a noun. It doesn't tell you, it tells you the parts of speech. It tells you what role each word has, but it doesn't really say that noun is doing something, for example, or is associated with the verb. Therefore, in some layer, you need the dependency parses. So that's what parsing means, right? OK, so that's part of speech. If you want to go from the lowest level to the higher level, perhaps a POS is one of the very, very low level ones. And then parsing is the next layer. And then the semantic rules would be the next layer. OK, so this is the architecture. This is by far the most important slide of this presentation. I'll try to spend as much time as possible to clarify everything that's going on here. In future slides, you see equations according to this architecture.
For POS, is it just like, does it come from a dictionary or does it learned?
So, part of speech tagging, syntactic parsing, and semantic rule labeling have been traditional tasks in natural language processing because only then you could do semantic analysis and a lot of other downstream tasks, including machine translation, traditionally. For all of those tasks, we have gold standard, for English at least, and for a lot of other languages. That means we have human labels, as well as we have POS taggers, very established and high-performing parsers, dependency parsers. So we have both tools that can predict those and also gold standards that can inform any architecture that we built. Thanks for the question. All right, so this is the architecture. Basically, it starts with a sentence, a tokenized sentence. I saw the sloth climbing. You have one layer of multi-head self-attention. We get to the details of what it is mathematically. Then you have this joint space of predicate and part of speech tags. This was asked earlier. So basically what it means, if we have two, in an artificial language, let's say, we have two part of speech tags in the vocabulary of the language, and then we have, I don't know, 3 types of predicates. The entire space would be 6, for example. You can see, do I have it there? Yes. So the label would be tag, predicate, right? So it's just a joint space of the two. So you have one label per each tag and predicate prediction, right? So you're not predicting them separately. each tag, so part of speech tag predicate combination is one label. All right. So multi-head self-attention plus a feed-forward layer. So after each self-attention, again, we get to the details of it, we apply a feed-forward layer. Self-attention, now let's think of it an attended overrepresentation of each sentence, each word in a sentence. So each word, in a high level, we go into details soon, each word has, is technically a weighted sum of every other word in a sentence, right? Let's think of it that way for now. And why is that important? Because then each word is informed of every other word in the sentence and its relationship, right? And that's how self-attention tackles these stacks efficiently, even prior to this work. Okay, but we'll get to the details. So joint space of prediction, so you make this prediction, right? And then what you do after is let's say you know that such and such is a predicate, and the rest of the sentence have these part of speech tags. Okay, you know this, right? Then you do know that what representation is associated with that predicate and that part of speech tag. You transfer that representation to this latest layer. Don't mind skipping these two for now. And you form this predicate representation. Okay, let's leave it at that for now. Go back to the previous layers. You have a direct connection to a syntactically informed self-attention layer. So these two are one of the most important part of the architecture and the novel parts of it. I'm not sure if I should talk all about it right now or a bit later. So let's skip this layer for now. We get back to it. We have another multi-head self-attention on top of it. So let's think of it as just receiving some syntactic information. Or trying to tackle a syntactic task. Basically, on a high level, this layer has one attention head specifically paying attention to syntax. And we'll see very shortly what it is. So anyhow, and then over here, you predict your, you form your semantic role representations. You have two feed-forward layers lead to linear representation, and then you perform a bilinear operation to predict the thematic roles, another name for semantic roles of your sentence. So let's decode that a little bit, because that's the end goal. So basically, it's saying for each word, it's saying what the predicate is, right? So BV would be the predicate of this word in the sentence. Oh, this word, though, is the second word. That's fine. So for each word, you decide which predicate it's governed by. And by that, let's think of it as verb for now. So then you know what, for example, climbing is governed by. Oh, that's another predicate, so it's tough. Okay, so we know, for example, that sloth, I saw the sloth, is governed by, and by governed I mean who is its main verb, by saw, right? So sloth is governed by saw. We know that. For the, we also know it's governed by saw, or and some theories sloth itself. Doesn't matter. But for the verb, and we know that I, for example, as a subject is governed by saw. So if you look at any of those, it should have saw, which is here, second position, as the predicate, right? Saw as predicate. For saw and climbing, though, we apply the self group. So if a word is a predicate, it is governed by its own, just architecturally, so that we have some representation. We'll see why it's important shortly. Okay, let's see if I say everything I wanted to say. Yes, so we have J self-attention layers. So J would be the number of self-attention layers. R, I talked about it. So R is the representation input to decide on POS tagging and predicate detection joint space, which is also the predicate and role embeddings. Oh, I did talk about the embeddings. We used maximum likelihood and SGD for optimization, stochastic gradient descent. And R sub T would be the per class scores of the linear classifier. So this is just a linear classifier that decides which one of these is a verb, subject, object, so a part of speech tags, as well as which one of them is or is not a predicate. For climbing, you see that the output is O and O. What that means is that those are not even in the picture. For climbing, those are irrelevant. For climbing, what matters are the and slop. And those are arguments of climbing, right? So argument 0 and 1. That's one way of encoding the semantic role information. They correspond to those themes, patience, and receiver, goal, and those things that I talked about as semantic roles earlier. All right. So we'll get to the details soon. This layer I want to talk about more. All right. So this is layer P. Okay. It's one attention head in layer. So only one of the attention heads in layer P attends over the parents per token. So basically, what it means is that you have these words. In layer P, one of the attention heads, we want to make sure that it's attending to the right parent. In a dependency parse, a right parent would be the verb that governs that word, right? So let's say these are the output of the attention heads. You have your attention head parse attending over saw, right? As the output of the parse. The rest, so we want our model to pay attention correctly to saw and force that into the representation. The final in self-attention, usually how it works is that you have multiple heads. So multiple, sort of think of it as almost independent neural net architectures. And at the later point, the outputs would be different vector representations per word will be concatenated. So if you have 8 attention heads, the final representation will be the concatenation of 8 representations output by each self-attention heads, right? Okay, so we're only forcing one of them to pay attention to saw specifically. Normally, how it would work, every one of them would look like this one. Every one of them, to some extent, attends to this one. To some extent, attends to this one. Pays a lot of attention to this one. This other head likes to pay attention a lot to this one. Totally free in parameterization. This one, we want it to pay attention specifically and solely to the governing word, which we call the syntactic parent. The rest have to be zeroed out. Okay, so that's what's happening here. So we have 2 layers that are giving us syntactic, forcing the model to encode syntactic information. One, who's my verb? The other, what part of speech tags there are, and what predicates there are. So it's forcing this first layer to encode all that information. That layer and its parameters and the result of that layer is shared with the semantic role already, right? And that's very important. Just to finish the thought, so the syntactic information is conveyed both towards the semantic role labeling part, as well as the predicate embedding. You had a question?
So what is the reason of having the two words saw and climbing as the end, as the output of this pipeline? Are these two the only kind of the governing?
Yes, those are. So this could be thought of as a nominal predicate. Feel free to, for linguists out there, feel free to correct me on YouTube. So climbing would be the nominal predicate, and my understanding is that because it's technically a name. Again, correct me. And saw, but it has a. Let's say, let's think of it this way, and I hope I'm correct. Let's think of the nominal predicate as, I had this as a discussion point, as I saw a dying man, right? So forget about saw, which is one governor. Dying in some way governs. So who's the object of dying? It's an adjective technically, right? But who's the object of it? And so that's what I remember from my linguistics. But let's think of it that way. Mostly they are the verbs. So each output, then, to answer your question directly, each output is okay. You have a verb, BV or predicate. Okay, that's the purpose of semantic role labeling: getting a predicate and saying what are the arguments of that predicate, what it's affecting, and what type those predicates are. So my understanding is that 0 and argument 0 and argument y, or these I and b's, they refer to different roles. So patients, agent, which is the doer, right? So I is B, is probably the doer, and then arg1 slot must be the patient, right? So these both are the patients. This sloth, it forms a noun phrase per se, or noun phrase, and I would be the agent, so the doer. Does that answer your question clearly? Okay. Okay. All right. So, yeah.
So if you force one of the attention heads to be like really one slot, how can it learn? Because it seems like something that's not smooth. Like, how do you backpropagate?
So it's a supervised learning. So at this point, we want it to present those. It receives to have those. It receives a cost function. It receives a cost function if forcing it to have this output. So basically, this is not forced manually. In training, this can do as well as all of these. But if it doesn't perform this one right, which is this exact representation, it will receive more. It will receive more penalty.
Okay, so if I understand correctly, that it's a normal attention head, but with an extra penalty in the cost function if it's not the correct.
Yes.
Okay.
Yes. Very good question, because it could be a confusion point. The point that I mentioned earlier, forcing the attention for gold standard parse series doesn't relate to it right now during the training time. During inference and test time, then you can actually force it, because you have, again, it's just attention, and you can just you know what the labels are, so you just set everything else to 0. But during training, you want to train it to perform that way. Good. Is that clear?
Yeah.
Yeah. Okay. All right. Beautiful. So a pointer comparison with all architectures. Typical earlier models use token-wise tagging per predicate per sentence. I think I sort of hinted towards that. So you get your predicate, you're encoding per your predicate, and it's computationally just more costly. Okay, so mathematically, this is a res self-attention layer, residual self-attention layer, plus scaling. So you have your self-attention. You apply it on the representation of the previous layer.
you spell them out because people don't see?
They don't see my hands? Okay. You have two terms inside ln, which is layer normalization. The s sub t j minus 1 plus t of st j minus 1. St j minus 1 is a representation of the previous layer. You apply your self-attention by it, you have some output, right? And you add it to the original st minus 1 and stj minus 1, sorry, the representation of the previous layer. So it's a residual connection. You directly also connect it. You add them together, and there you go. You have your s sub t. Basically, it's just a residual layer that carries over. It's a skip connection that carries over representation of the previous layer, which helps us these days train deeper networks. Okay, so that's it. Let's see what else do I have here. So H is the self-attention heads at each self-attention layer with residual connections, I mentioned. So you have H heads. The results of the heads are concatenated to form the final self-attention representation, as mentioned earlier. We use something called inverse dot product attention, where you scale your weight by the inverse square root of embedding dimension size, and then normalization. So that's your that decay to the 2 minus half is our scaling factor, and Q and K are our query and key representations, which you perform a softmax on it and get an attention. So traditionally, to give you some insight as to how this works, in self-attention, again, you can go back to our previous videos on self-attention on our website. But basically, you can intuitively think of Q, query, as querying what representation do I need to have. And jointly with key and K, they usually are combined into an attention, apply the softmax upon them. So basically, you have a word in a sentence for each attention head. You can have multiple. For word in a sentence, you have a Q representation for it. You take that Q, you compute the dot product of that Q, with every other word in the sentence, right? And for each other word in the sentence, it gives you an outcome. You scale that, and you apply softmax on it. Softmax forces it to have values between 0 and 1. Probability, and then and there you go. You have your attention. It's a probability of how related each word is to every other word in that sentence. You multiply that attention by your value vectors per each word, and you get the attended over representation of that word. So V vectors are represented are kept only to that purpose. So M would be your final representation, self-attention. For more details, refer to our videos or ask me during the discussions. Okay, so the row of T, M to J. So J, remember, is your layer, and related to sub H, related to your attention head, is your self-attention representation for token T at layer J. Which is the weighted sum of the V's, or values, presented to, so this, as each self-attention, so remember we have stacked layers. At each layer, you pass the self-attention result to the next layer, to two feed-forward layers, or you can think of them as one, with two leaky ReLU activities. So either one with two leaky ReLU activation functions, or you can think of it as one with two ReLU activations. Anyhow, so you have your rectified linear unit, and voila, you have your representation per layer. That representation is, the dimension of that representation is similar to the input dimension, so it can be looped over as many times as you want. You can go as deep as you'd like to be. Okay, let's get that. Let's get to that syntactically informed self-attention head. So we replace an attention head by the deep biaffine model from, I hope I pronounced the names correctly, Dozat and Manning, 2017, trained to predict dependencies. Okay, so we have an attention for parse, specifically as mentioned earlier, which is our parse attention weights at layer I. And taking as input S super I minus 1, K of parse, parent Q of parse, K of parse, denoting the parent. This is very important, so I'm going to repeat myself. And Q of parse, the dependent. So the brilliance of this sort of architecture is, okay, I want to use self-attention for parsing. How do I go about it? So previously, you had query, key, and values all representing different values of words, different representations of words, right? Now, what they're saying is that, okay, let's use it differently. Let's have the same exact architecture, have an input Si minus 1. I think they indexed it I because they wanted to be separate from the J layers. It was a bit annoying at first, but I understand why, and I actually like it now. And you have K parse, so the K representation, instead of looking at every other word, is targeted to be the parent of that specific word, the parent, the governor, or a predicate, right? And Q parse would be the dependent. So basically, you start from query, right? You start from, oh, I want to know what this word is a dependent of. Who's my parent, right? You go around all the words, you multiply that Q by all the Ks, you get multiple values. What you're training the network to learn is that for the parent that's the actual parent, you have the highest attention scores, right? Similar equation as was shown earlier. Oh, this is here. So A parse, softmax of your Q parse, and K parse transposed, right? And this U head is just the parameters of your network, which is the bilinear affine transformation. Okay, so the difference from this part of the architecture and the rest of the self-attention models is that you don't use dot product here. Previously, you would use your dot product, right? Okay. Okay, so a little bit of notation. So A parse of T and K would be the probability of token T having head Q. And A parse of T would be the distribution over heads over token T. Distribution over heads for token T, sorry. Root token has a self-root, as mentioned earlier. So if it's a verb, it refers to itself. It needs to pay attention to itself. And it results in a directed graph. So probability of Q being head T, given X as your input, equals to A parse T for T and K. Yeah, and as mentioned earlier, so this is what your network learns, but during runtime, test time, inference, if you have a better parser, you can just force the attentions to be to pay attention to the verbs that you know by manipulating the attention matrix that you know are the verbs. All right. So the last bilinear transformation, I think this is the last equation. Basically, if you remember in our architecture, this is here. We're here right now. So in the bilinear side of the penultimate layer. So where you have two feed-forwards of S predicate and S row. And you get your representations out of those feed-forward layers. per each one. Now you want to see how they merge. So basically, how do I merge these two information flows coming in from your semantic role labeling, semantic role embeddings, and your predicate embeddings. Again, another bilinear transformation, and getting your final representation, which then you can classify your semantic roles with final classification of semantic roles. All right, this was the model in architecture. Next is a break, and then we come back with the results.
Okay, we're on.
Okay, thanks very much.
We're on.
Yep. All right, so I'm gonna add, so I missed the cost function in my slides. I'm just gonna quickly mention them. So you look at your, let's go to the architecture. So it's you can look at the paper. Not sure which page is it. Right above the related work 3 sections. So section 2.5 training. So it's basically a combination of the cost over here for your joint space prediction, plus your labels, the cost to get those labels right, and detecting the heads, the attention heads right, as well as, I think I mentioned them all. It depends. Also, the dependency parts right. The dependency parts right. I think it's also here. Yeah, that's the attention. The joint space, I mentioned dependency. Okay, I mentioned them all. So semantic role, dependency parse, the attention head, and the joint space. Okay, all right. So that's the cost function. Sorry for missing that slide. Okay. All right, let's go to the results. So again, feel free to stop me if anything is unclear. They used 2 embedding types, so standard embeddings and Elmo embeddings. If you want to know about Elmo embeddings, do take a look at our video on Elmo. So basically, a brief summary is Elmo is a task-specific representation per embedding. So your representation, your Elmo embedding representation will be different for semantic role labeling as opposed to syntactic parsing as a different task, or machine translation as a different task, right? So that's what Elmo is. Take a look at. We have a really good talk on that. So they alternate between these 2 embeddings. They also alternate between Lisa, vanilla Lisa, without using any very good parsers external to the architecture. They use it with the external parser, the results of which added to the architecture using the force attention layer, as I mentioned earlier. And alternatively with gold standard, so human labels, right? And they also compare it against the self-attention without the linguistic information added, right? I think it's still their interpretation of the self-attention architecture. And they compare with, obviously, the previous works, given for which task and which data set, there is results available. You can show that, you can see that, first of all, with gold, you can see the jump in performance from 83.58, which would be the best other one with DNM. So DNM is just that article that we talked about from Professor Manning at Stanford. So with that parsing, you already beat state of the art. But if you provide gold, then you see almost 3 points jump in F-score, which is big. Basically, the higher you go, obviously, the harder it is to increase, right, in F-score. So this is the dev WSJ test and Brown test of the data set.
Did you say what those tests are?
So if I'm, so there are different portions of the data set. All of them are semantic role labeling tests. If I remember correctly, the Brown test was out of domain. I think that's the difference, and that's why you see the collapse in performance. Basically, the test set, the domain of the test set is different from what it was trained on. We still expect it to outperform other architectures, but you see that everybody has a problem with it. That was the problematic, one of the problematic cases where they tried to add syntactic information. Syntactic information is very domain dependent. So I don't know, in medicine, you could see complex, long words. In some other field, you could see complex phrases. So it's real, syntactic information is domain dependent. And this is with Elmo. You can see that still their architecture is outperforming every other architecture. Sometimes adding this syntactic parse from DNM helps and achieves the highest performance. Sometimes it doesn't achieve the highest performance. As you can see, Lisa Vanilla beat the F-score for the dev with Elmo representation. But still, you can see that adding gold substantially improves the performance. But they're not bolding them out because, well, they want to compare with their own architecture and predicted values as opposed to gold. OK, so this is precision, recall, and F1 on. OK, so there are two data sets. So this was all Cornell 2005 development and test set, which has portions. This is precision, recall, and F-score on Cornell 2005 with gold predicates. So gold predicates, so if you remember the architecture, it did quite a few things at the same time. It decided what the predicates are, what the governing predicates are, what the part of speech tags are, and what the syntactic parses are, right? Now, if you feed in the predicates gold, which you can do with this architecture, this is what happens. So if you do that, and also say on the WSJ subset test set, if you add gold predicates, you can see that their system informed by the syntactic parses. So these are not gold, but DNM parses will beat state of the art. It seems like by more than almost 2.5 F-score. If you on Brown test set, you see also on out of domain test set, you see also the same a similar increase. All right. Okay, so let's look at table 4 for now. Parsing labeled and unlabeled attachment and part of speech accuracies attained by the models using SRL experiments on test datasets. Subscript G denotes glove, and E, Elmo embeddings. So these are parsing and POS accuracies. UAS and LAS, let me see if I can remember this here. So I think LAS is labeled attachment score, and UAS is unlabeled attachment score. So the difference between the two are in syntactic parsing, sometimes you can just get the arguments right. So this verb is governing these two words without specifically saying what syntactic roles they carry. Sometimes you can actually have the labels. So that's the label. That's LAS. And LAS is, well, harder because if you don't get the labels right, you don't get it right, right? But if you just get the parses right, dependency, what depends on what, it's a bit easier. So you can see that the performance LAS is a little bit lower. So you have WSJ, again, Brown and Cornell 12. Cornell 12 is the 2012 version of the data set. And those are basically part of speech tag and parsing accuracies. Let's see. So what's the best? So per category. So let's look at WSJ for now. 94 for LAS with DNM is the best performing one. For UAS, again, DNM best performing one. For POS tags, they can't use DNM because it's one level after part speech tagging, and that would directly use that information. So Lisa G with I think G was gold standard. Oh, Glove with Glove embeddings underperforms Lisa with Elmo embeddings, which is task-specific embeddings trained. So nothing surprising over there. For Brown, we also see, oh, interesting. So for Brown, we can see that with, again, with Elmo, actually with Brown, you see that with Elmo Lisa with Elmo representation actually outperforms the DNM, syntactic information added, which is interesting. For the POS also, you can see that Elmo outperforms, as seen earlier. Okay, I'm going to go to the other table. Let's go to table 5. Predicate detection, precision, recall, and F1 on Cornell 2005 and Cornell 2012 test sets. So this is just part of speech tags. Remember, these are all part of the cost function, and these are all the tasks performed by the model. You can see that Lisa substantially outperforms He et al. On precision, and quite well by 2 F1 scores on an F score. Brown, again, you can see that it performs by 1 and something F score, and quite much, around 6% precision. It doesn't have as much as the recall. And for the 2012 data set, you see that it has a high F score. So really, I don't think it's really comparing with anything over there, but it's good for future comparisons. Okay, on the right, you can see table 3, precision, recall, and F score on the Cornell 2012 development test set. Italics indicate a syntactic upper bound obtained by providing a gold parse at test time. Okay, interesting. So yeah, so basically they're also writing gold. So it seems that for most of them, let's look at the first table with Glove embeddings. DNM parses get the best performance. Gold beats it. For Elmo, Lisa gets the best performance on F score. Test set, DNM achieves the best performance.
Is it safe if you say that in general, usually when we have Elmo, Lisa itself works better than others. And in other case, in Glove case, SA is better than Lisa, like vanilla Lisa. But when we add DNM, it's Lisa with DNM becomes the best.
Yeah, that's a good observation. Thanks for adding. That seems about it.
Could
Shall I? Yeah.
DNM be added to the one on the top, the he at all?
No, because that's the previous architecture. If you add it, you're basically recreating Lisa.
And there is no way to do that because we don't have that
Modular
head.
That
separate
extra head.
yeah.
If you add it, then you have Lisa.
But this DNM is the parser, right? It's not the
Correct.
syntactic attention head that you mentioned previously.
Correct.
The parse, yeah.
But if I'm not mistaken, okay, hold on. If I'm not mistaken, it actually uses a similar syntactic attention to achieve parsing. And they kind of...
Yeah, so they are in two like layers. So in the first layer you have one, like this one, and then in the next layer you have the other one. So if you look at the structure, it's kind of both have like output, and that's why you can train, multitask train on both.
Yeah. And if I remember also correctly, they even keep the parameter of that layer very similar to that to DNM work, to Manning 2017 work, to make sure it has similar performance. But it's a heterogeneous, almost heterogeneous layer added. If you take that out and build your model, then that's probably DNM. I'd encourage you to look at the original papers. But very good question. Very good question. I didn't mention that. Okay, great. Over here, what's going on? Table 6, average semantic rule labels, F scores on Connell 2005 for sentences where Lisa L and DMD parses were completely correct or completely incorrect. So basically, it's comparing the two architecture, Lisa standalone and Lisa added DNM. We can see that on the left most column, L plus / D plus, for 79% of the cases, both are completely correct. Hold on, is that a correct interpretation? Right. For sentences, Lisa and DM parses were completely correct. Oh, okay. So yes. So those are the scores where the parses of both methods are completely correct. So the parses are correct, and these are the average semantic rule labeling scores. So again, these are semantic rule labeling scores, and the first column is where both. This is to see how much syntactic information sort of matters, right? So the first column is both of them did correctly, and let's see how what the F score average F scores are. Where Lisa did incorrectly and exclusively incorrectly, and DNM worked correctly. These are the average F scores. Vice versa, third column, and none of them working correctly. These are the average F scores. A lot of insights, I think, can be generated from this table. One would be that with gold parses, well, obviously they perform well. But I think in general, when the syntactic parses are incorrect, you can see that the when they both are, let's compare the first and the last columns. So when they both are incorrect, they perform worse than when they are correct, as intuitively you would expect. And the ones in the middle, you can kind of see which one is more informative to some extent. So for the model, Lisa itself. So when Lisa is correct and parsing correctly, you can see that it performs really well. It's interesting that when Lisa is incorrect, but DNM is correct, it on average performs much less comparatively. Okay, on the right, figure 3, performance of Connell 2005 models after performing corrections from Hay et al. So basically, they are looking at the syntactic parses. There are a few things that can go wrong. One of which is the span of those sort of. I think, are these POS tags or parses? Masood, if you can look at it. Span boundary.
Yeah, those ones are parses.
Those are parses, right?
Okay.
Okay, I see. So if you only correct the labels where the labels are incorrect, you can see this much improvement, 2.5, more than that actually, 3 or 4 F score. If you move the core argument, so is that where the core argument is misplaced?
Yeah.
Okay. You correct that, you see a bit of improvement. If you merge the spans to reach the correct span of the arguments, so remember, everything is predicate and then arguments. So arguments could be patients, agents, whatever, or syntactically. Verbs, objects, and subjects to be correct. So if you have the wrong span, sometimes if merging, like there it was, let's say your object was a phrase, say the man. So the man got, I don't know, attacked. And if you, or the man attacked, I don't know, the kid. That the kid, that's so wrong. If you only label kid as the object, for example, that's a span, that's an incorrect span. Right? You want it to be the kid as the object, for example. Right? It really depends on your syntactic theory. There are many competing syntactic theories. All right, so that's the span. Sometimes you split the span. You say, I don't know, there is some word before the correct span you included. You get rid of it. That's fixed span boundary, or sorry, split spans. That's overall fixing it without the previous corrections. That's dropping an argument. So whenever it says an argument, but there is no argument, like those O's, if you recall. And adding an argument. You missed an argument. You missed the fact that this is an object. You didn't label it. You label it, you see how much it performs. So this is a substantial improvement. Okay. Okay, here, one more. So present an account of split merge corrections performed in figure 3 by phrase type. So now you see which one syntactically the model is struggling with the most, which is the PP attachment, which is hard. And the reason for that is that PP attachments they can move about. I can say with good intent, I asked you, are we still live? Okay. I can say with good intent, I think the fuse is off or something. I can say with good intent, I told you to read the paper, right? Or I can say I told you to read the paper with good intent. So that with good intent can really move about in the sentence, or any other prepositional phrases. And so you can see that's a really hard task, and you saw earlier that why it was hard. NP is next, verb phrases are next, and so on and so forth. So pronouns, adverbs, and S bar. What was S bar? I don't remember S bar. Yeah, I don't remember that one. Oh, S bar, I think it's a sentence. Yeah, okay, I remember. If I'm not mistaken, is this if you get the entire sentence right? But look at the paper. And other syntactic mistakes. All right, thank you very much. Any questions or comments? Feel free. Yeah.
Earlier, there was a question about parts of speech and whether or not it was a dictionary lookup was available. Does that cover the situation where a word can have different parts of speech, and you have to get it right?
Could you elaborate a little bit? I'm not quite understanding.
Well, like, I don't know, stamp. It could be a piece of paper you put on an envelope, or it could be that you're stepping on something. So the word has different parts of speech and different
Correct.
meanings, right?
Correct, yes.
Does this have to resolve that as well?
Yes, so
Okay.
we're forcing, so the model itself, let's look at one of the tables.
So then you can't have a dictionary lookup, right? Because it would depend.
You can or you cannot?
You cannot.
So why would dictionary lookup matter in this
Well, I was
context?
just wondering how to, I mean, that was the question was, where do you get the label for
I see.
part of speech from?
Gotcha. Okay, great question. So as hinted earlier, these are, so part of speech tagging, syntactic parsing are established tasks in NLP. So we have tons of, for each syntactic theory, we have a lot of annotations that people use. Dependency parsing is just one of them. So we have humans actually sat down and annotated all those correctly, specifically linguists. So gold standards. I'm not saying that there is no error, because humans are also prone to error, but they're really high accuracy. It's not dictionary lookup. Okay, good question.
Correct me if I'm wrong, but like when you use Elmo embeddings with Lisa, so Elmo embeddings can take care of the situation that was just described, right? For instance, the word bank has different meanings, right? Based on.
No. So it's a different. So what the question that was mentioned was, what if you get the predicates wrong? And I think by the results that we showed is that if you get the predicates wrong, it will negatively affect your performance, right? If you get parses wrong, it will also negatively affect the performance. By the previous studies and this study, Elmo, what it does, it's task-specific embedding. So the word stamp, being the verb itself, for the verbal situation, it has different embeddings for semantic rule labeling as compared to dependency parsing. And hence less prone to error risk. Yeah.
I just have a thought came up after you mentioned annotate, because when you do part of speech, you labeling for the sentence, you are annotating every object in the sentence. So then is it like analogy in image for object detection? So you are annotating each object in the image. So then in this case are the two methods in text sentence annotating and image object annotating, like sharing the same kind of framework?
Yes, that's precisely correct. So for people coming from vision background, these data sets are very similar to like CFAR or images, in the sense that you have those boundaries. So some humans have sat down and set those boundaries. So for images, if it's objects, it's object boundaries or bounding boxes. You have vertices usually of those, done by human, because that's what we learn from in a supervised manner. Yes.
Those who haven't asked questions?
So discussion?
So I think a few points. I think we went through them when we sort of talked about the tables, but feel free to add if any discussion points came to your mind. I think ultimately, let me reiterate the most important and exciting parts of the paper. So one is using another architecture, another self-attention architecture, to inform syntactically your self-attention architecture, and doing it successfully. The other is increasing substantially for the amount of F scores that that state of the art is at, the previous works using that architecture. What else? The other would be that would gold standard parsers actually help, or in general using gold standard syntactic information would help. Yes, indeed, and by much. And also enabling other pipelines, other NLP pipelines to be used in your model to just get better performance, because ultimately if you have a chatbot, a machine translation system, all you care about is better performance. If there is some way to have it perform better, well, you just want to add that architecture to your architecture. I'd like to draw a comparison with how the brain works. The brain has like sentence for certain centers that arguably process syntax and semantics differently. Broca and I think it was Wernicke, if I'm saying those correctly. And that is similar to what's happening here. So it seems that we're having parts of the architecture specifically addressing syntax, although very similar in nature to the rest of the architecture, as the brain is just neurons sending messages to each other, right? Same thing is happening here. The architecture is very similar, but they seem to be paying attention to different things. I thought this was an interesting comparison to draw upon. Masood, any other points you'd like to, if I haven't covered already?
I think you covered everything. The only thing that is like interesting to me is comparing the vanilla self-attention to Lisa using Glove, which is usually working better. Obviously, having this fantasy to use other parser is very important, but if you don't have that information, essay is already doing a good job, comparable in most cases with even DM. Mm-hmm. So that was like interesting.
Yeah.
Yeah. Another sorry, go on. So you talked about the modularity. Can you clarify that by like going back to the arc figure that has the architecture and sort of what can you plug in where?
Mm-hmm. So if you look at this syntactically informed self-attention layer, right? And to some extent this one, but this one was the I think the one that they use self-attention to add that modularity. So this layer is basically, I'm just sort of unwrapping this layer. Is basically this, right? So what's happening is that you can take out one of the attention heads in this layer that are multiple. What attention heads are just different. If you're, I hate to say that analogy, but it works for some. If you look at ensembling methods, you have a few methods. They all vote differently, and then you ensemble, and then you use all the information about all different models. You can sort of think of as attention heads in that regard. Like that's just an analogy. Obviously, mathematically, they're not much like too much alike. So you grab only one of the self-attention heads and force it to learn Syntactic dependencies, basically over here, which is my parent. Which word is my parent? You can then replace that by if you have gold standard, add inference time. You can get rid of that. So that you've trained this, right, previously. But in May, like depending on how much you could train it well, like it could do well, we saw during the results that usually taking this out and adding hard attention to it, hard-coded attention to it, which comes from another parse or gold standard, substantially improves the performance. Yeah, absolutely.
Yeah, so during your talk, you mentioned that semantic role labeling is quite domain dependent, right? So if your domain changes, so you need to do training and everything, like for each domain, you need to have like a different model, right?
I mean, it just performs lower if it's not been. As with most of, I think, supervised learning, usually if you introduce a new domain, things both syntactic features of the domain may change, and therefore your performance may drop. So for most of these, you see in Brown test, you see a drop of performance. It's not going like 10%, right, or 10 F scores. It's going a few like 5 to 6 F scores. More than that, like 10 F scores, 12 F scores less, right? Yeah. So to some extent, yes. Okay.
Any other points? Anything from online? No. Okay, then let's thank our speaker, Asan, and also Masood, our facilitator, and then also Maria.